Hello everyone, myself Sharda Mase, VIT Pune. Today we'll continue with examples of modeling. In last lecture we have done with one example radioactive decay. Today we'll continue with similar type of example. Very first is rectilinear motion. It is a motion of a body along a straight line. Consider a body of mass m which starts to move from a fixed point, say O, along a straight line OX under the action of a force F. Now as that body moves, after a certain time, say that body is at point P where distance OP is x. Then velocity is given by rate of change of displacement with respect to t, and acceleration of that body is given by derivative of v, or you can say d by dt of dx by dt, which is nothing but d2x by dt square. Also we can write this acceleration as d by dt of v, or by chain rule dv dx into dx dt, or that can be written as now v into dv by dx. Thus, acceleration can be represented by dv by dt or d2x by dt square or dv by dx into v. Now, by using Newton's second law of motion, we all know that force is nothing but mass into acceleration. So if I substitute that value, it gives us F is equal to m into d2x by dt square. By mistake that t and x are interchanged, but it's d2. Read it as d2x by dt square. Then by using this, now we'll solve an example. Consider a body of mass m falling from rest to the force of gravity and an air resistance which is proportional to the square of velocity. If it falls through a distance x and possesses a velocity v at that instant, prove that 2kx divided by m is equal to ln of a square divided by a square minus v square, where m into g is ka square. We'll look at the solution now. First of all, we'll form the differential equation. Then we'll convert this given situation into differential equation. Then we'll solve that differential equation by using suitable method, and then we'll prove the required result. Now, by Newton's second law, equation of motion here given by m into v into dv by dx, that v into dv by dx term is nothing but your acceleration term m into a. Now if you look at this system, force mg acts in downward direction, that you can say force due to gravity, and force k into v square, that is, as given in the information, air resistance is proportional to the square of velocity. Here v square of velocity, and the term k is the constant of proportionality, and negative sign shows that force is in upward direction to the force exactly opposite to the force mg, which is in downward direction. Hence we get m into v dv by dx, which is equal to mg minus k into v square. But information that we have is mj is equal to k into a square. Substituting that value, we get m into v dv by dx equal to k times a square minus v square. Rearranging the equation and separating the variable, we get v into dv divided by a square minus v square is equal to k by m. Integrating this new equation and solving that integral, we get the integration of v upon a square minus v square as 1 by 2 with negative sign ln of a square minus v square. And integration of RHS is k by m constant, integration of 1 is x plus constant of integration. Now how to determine that c? Initially, when distance is 0, velocity is also 0, then using equation 1, putting x0 and v0, we get c as negative 1 by 2 ln of a square. Substituting this value of c in equation 1, we get simplified equation 2kx divided by m equal to ln of a square divided by a square minus v square. That is the required result. So what we have done throughout, given the physical situation, by applying mathematical terms and laws, Newton's second law, we obtained the equation of motion, that is formation of differential equation, and we have solved that differential equation by variable separable method, and then integration gives us required solution. So overall, we have applied one by one different steps of modeling. Next example that we'll see is electric circuits. Consider the circuit as shown in the figure. It contains an electromotive force supplied by a battery or generator, resistance R, and inductor L in the series. Now, very first step we'll do is formation of differential equation. From Kirchhoff's law, we know that voltage drop across the resistor is I into R, while voltage drop across inductance is L into di by dt, where I is the amount of current flowing through the circuit at a time t. Now using Kirchhoff's voltage law, sum of this voltage drop is equal to the supplied voltage, say E in this case. What we can write hence? Sum L into di by dt plus IR is equal to E. You can observe we are getting some differential equation. That differential equation can be written as di by dt plus I into R divided by L is equal to E by L, which is first order and first degree LDE. And as we know the procedure to solve this kind of differential equation, we'll proceed with that. Here, integrating factor is e to the power p dt, that comes out to be e to the power r into t divided by L. And if we look at the solution is given by, here unknown term is I, We are solving for I into integrating factor is equal to q into integrating factor plus, I forgot to add integration of constant, plus integration of constant, which gives us the solution I into e to the power rt by L is equal to e by r e to the power rt by L plus k, where k is arbitrary constant. Now what happens at initial condition? When t is 0, I is 0, which gives k as minus e by r. By substituting that value, I can be written as e upon r into 1 minus e to the power minus rt by L as the amount of current flowing through the circuit at a time t. One of the interpretation of above value of I, as t tends to infinity, e to the power minus rt by L tends to 0, and we get maximum value of I as e by r flowing through the circuit. So this is how we have modeled given electrical circuit, particularly LR series circuit, in the form of differential equation, and we have solved that differential equation and we got value of current flowing through the circuit at some time t. One more example, model of population growth. Here, to model the population growth, assumption that we are going to follow is population grows at a rate proportional to the size of the population. Let's identify and name the variable in this model. Here, let's identify first of all variable that we are going to use in this model. Let t denotes the time, which is independent variable, and p be the number of individuals in the population. How we are going to form here differential equation? Now, the rate of growth of population is the derivative dp by dt. So our assumption, that is the rate of growth of population is proportional to the population size, is written as dp by dt is equal to k into p, where k is proportionality constant. Now, the growth rate increases as the population increases. How? We'll consider here k as greater than 0 and we'll rule out the case p is negative. By ruling out that case p is negative, we always have that derivative term k into p as greater than 0, which says that function is increasing. That is, here population increases with respect to time. That is, growth rate increases as population increases. Now we know this kind of differential equation. Similar thing we have seen in radioactive decay. Solution of this kind of equation is exponential function. So I'll write that solution as p of t is equal to c times e to the power kt. Graph of solution when the c is positive and t is greater or equal 0 is as shown in the figure. You can see exponential curve for c positive and t greater or equal 0. Thing to be noted is this differential equation is for modeling population growth under ideal conditions. If conditions are different, there are some more number of variable which affects the population, In that case, this differential equation may get modified because of number of different parameters affecting the population. But as far as ideal conditions are concerned, this is considered as population model. Thank you.